Hello my friends and welcome back to the You Can Do TV channel.
Heavy drills cut through concrete slabs, requiring full focus from HUMA operators. Hard to believe how controlled those drills move through such dense material. Operators from Concrete Cutting and Breaking Company set up on site just outside New Orleans for LA Ship's project. Logs of planning go into positioning each drill perfectly, because even a slight misalignment could mean trouble. Feels a bit like threading a needle with something the size of a car tire. The 60-core drill is engaged first, spinning through concrete with steady pressure. Water flows over the drill to keep it cool and reduce dust, letting operators maintain visibility and control. Operators adjust depth and speed as needed, ensuring every core is extracted smoothly. The 48 drill is used for smaller sections, complementing the larger cuts. Once drilling is completed, each core segment is carefully removed, ready for inspection or further processing. Conveyor carts and cranes assist in handling these heavy concrete pieces efficiently. The teamwork here is insane. Like everyone has their own superpower on site. End concrete core drilling may look straightforward, but it requires precision, patience, and constant attention to detail. Every spin, adjustment, and core pulled contributes to a successful project for LA Ship N. The Kincardine floating wind turbine off Aberdeen marks Scotland's first semi-submersible wind installation. Managed by Bourbon Subsea with Ryhoff's mooring systems, it's towed, anchored, and connected for offshore power generation. Hard to imagine cleaner energy looking this powerful. In underground construction, not every challenge can be handled by traditional drilling. The vertical shaft sinking machine, or VSM, takes over where normal equipment would struggle, cutting deep, stable shafts even in the toughest ground conditions. Each project begins with a shallow excavation and a concrete ring beam that guides and absorbs pressure from the process. Precast shaft segments are assembled, and a steel-edged ring acts as the cutting knife. Strand jacks anchor the structure, keeping the shaft steady while the VSM is mounted. The machine's cutter boom, connected to energy and supply lines, is lowered by winches for excavation. That crane lift looks smoother than you'd expect for a setup this heavy. The operator can choose manual or automatic cutting modes, adjusting the boom's reach and speed to suit soil hardness. The shaft remains filled with water to balance ground pressure and transport debris upward. A slurry circuit carries excavated material to the separation plant. Seeing soil and rock pumped up like liquid never stops being cool. As the shaft deepens, new concrete segments or in-situ rings are added continuously. When it reaches full depth, the machine is lifted out, the base is concreted, and grout replaces the bentonite layer, leaving a watertight, ready-to-use vertical shaft.
Concrete segments are heavy yet maneuvered into exact position. VSL Indonesia's crew positions a box girder segment using heavy-duty cranes and lifting equipment. Each segment is aligned carefully to the previously installed structure, ensuring the joints meet perfectly. Hydraulic jacks and temporary supports hold the segment as workers secure it with tensioned tendons. Before placement, measurements confirm the segment's orientation and level. Lubricated bearings allow slight adjustments during alignment, guaranteeing structural stability. Seeing such massive concrete elements fit together smoothly is quite something. Once tensioning is complete, the segment integrates seamlessly, ready to support the bridge deck above. Workers continuously monitor stresses and alignment throughout the process. The coordination between cranes, jacks, and crew looks like a well-rehearsed operation, almost like a puzzle coming together. Each segment is then inspected for proper connection and stability before the next piece is lifted. This methodical approach allows the bridge to rise efficiently while maintaining safety standards.
What kind of engineering lets a 600-ton block float and sink exactly where it's needed? Every caisson laid at the Tema port strengthens the wall that protects one of West Africa's busiest harbors. A deep trench, about 19 meters below the seabed, is first dredged to make way for the 74 units. Each caisson is cast on land, using nearly 1,000 cubic meters of concrete. That's a crazy amount of mix for just one block of wall. NN. Weighing around 600 tons, they're rolled onto a floating dock using inflatable airbags. Once there, the dock is moved close to the final position and submerged, allowing the caissons to float freely. Tugboats then guide them into alignment before being flooded to sink. Wild to think those things literally park themselves underwater. Finally, sand fills the hollow chambers and a solid deck is poured above. Feels like building Lego bricks for giants. How do teams install giant girder blocks on the sea using 600-ton crane vessels for the Kisonuma Bay crossing bridge? The first big moment arrives as the base block of the main tower is hoisted by a 500-ton crane vessel, setting the foundation for the bridge's stature. Each movement is monitored in real time to keep the massive unit steady despite sea swells. Next, the tall lower block, weighing about 890 tons, is lifted by a 3,000-ton crane vessel and connected to the base section. The scale of that lift makes your jaw drop. Even the slightest ocean breeze could shift tons of suspended steel, so coordination is everything. Then the 30-meter upper block, about 280 tons, is similarly placed, completing the tower segment. Every bolt tightened here carries the weight of precision engineering. With the tower standing, attention shifts to the main girder. Huge blocks are transported by barge and installed by a 600-ton lift crane according to the timeline. Crews work in synchronized timing, with tied schedules to achieve perfect positioning. A direct hoist system featuring double twin jacks and PC steel cables enables blocks to be placed in cantilever fashion, ensuring alignment and stability. The balance between hydraulic lift and cable tension defines the bridge's flawless line. After the girder blocks are joined, stay cables are pressed into place from above, using 600-ton pushjack equipment to secure the one-plane cable structure. You'd never guess how quiet these massive machines can be when everything moves smoothly. The bridge almost seems to breathe as tension spreads through every anchored line. It's like watching a puzzle of steel and concrete piece itself together over water. Every section is checked again before the next one rises, a rhythm of precision and endurance. Finally, the closure block is installed under nighttime navigational restrictions. A setting beam and pull-in device, along with the highest stay cables, adjust the joints before final closure. Inane. Crews operate under floodlights, making sure marine traffic stays clear below. That last segment locks everything into one continuous span, a tense but thrilling finale. Sandwiched between sky and sea, the bridge's 680-meter length and three-span continuous design, 160 meters plus 360 meters plus 160 meters, become reality on the coast of Miyagi. The structure gleams at dawn, a line of engineering stretched across the bay. Hard to imagine the calm surface once hid such an immense effort. Known. The result, a new landmark for disaster-resilient infrastructure, built with innovation and resolve. Now, every vehicle crossing it moves over a monument to teamwork and precision. You might never think a structure like this could rise so precisely over the waves. Some viewers say it feels like watching a giant come to life piece by piece. En Henen.
Follow the deck and cable installation as the bridge rises steadily, connecting District 7 and District 2. Spanning the Saigon River, the Phu Mai Bridge rises as a symbol of modern engineering and Vietnamese progress. The scale of those towers is hard to imagine until you see them in motion. The bridge was designed and built by the BBBH Consortium, combining Germany's Bilfinger Berger Civil with Australia's Balderstone Hornibrook. Drawing on past experience with large-scale cable-stayed bridges, the team managed the complex construction efficiently. Kind of wild how prior experience from Sydney and Panama shaped this project in Ho Chi Minh City. The roadway deck was assembled progressively, supported by cables attached to the towers, which bear the entire load. Massive travelers were transported across the river to replicate deckwork on the opposite side. That transfer almost looks like a giant puzzle being moved piece by piece. The deck closure was completed, linking District 7 and District 2. The bridge now serves as a key artery in the ring road system, connecting the southern Mekong Delta with central and northern Vietnam. Funny how a project this complex now feels like part of everyday city life. And every stage, from planning to deck closure, reflects careful coordination between heavy equipment, skilled operators, and project management. The teamwork behind this milestone really shines through in the time-lapse.
Transporting a 360-ton bridge is a rare engineering feat at Tilbury 2 Port, Tugboats guided the massive structure over 135 nautical miles from Rotterdam to Tilbury II, taking a full day of careful navigation. The first action on site involves positioning the bridge over the prepared abutments, using hydraulic jacks and cranes to lift and align it with precision. The sheer scale of this steel giant makes the coordination look effortless. Once in place, engineers check every joint and connection point, ensuring the bridge sits level and secure. Temporary bracing is added while permanent fasteners are tightened, and alignment is verified using laser measuring tools. Each section of the bridge is treated as a standalone module, yet must integrate seamlessly with the rest of the structure to support heavy port traffic. Watching the bridge settle into position makes it almost feel alive, like it's finding its exact spot. By the end of the operation, the first of 3 bridge components forms a stable approach for the Tilbury II roll-on, roll-off facility, ready to accommodate cargo operations. Concrete, steel, and structure crumble under the power of the Okada TSW 650XCV crosscutter. Built for serious demolition tasks, this 540 kilograms attachment mounts to excavators to tackle beams, columns, and thick walls efficiently. Operators guide the jaws over target material, ensuring alignment for clean cuts. NNN. Hydraulic pressure activates the crossed blades, shearing through steel and concrete in seconds. Seeing the first section split cleanly always draws attention. The alloyed construction of the blades provides both strength and durability, allowing repeated heavy-duty cuts without wear. NN. Placement is crucial. The operator positions the cutter to encompass the segment fully, then gradually applies force. As each beam or wall segment gives way, debris falls safely into pre-cleared zones. Guards and oil flow controls minimize the risk of recoil and maintain precision. A concrete beam snapping in one motion feels almost unreal. For awkward angles or irregular structures, the TSW 650XCV allows slight repositioning and micro-adjustments without losing hydraulic power, ensuring each cut remains controlled. After initial demolition, operators continue systematically, targeting remaining beams and connecting structures. The cutter's jaws clamp firmly on thick steel, slicing in a rhythmic sequence that prevents uncontrolled collapse. Lightweight hydraulic hoses combined with heavy-duty pressure valves allow continuous operation at maximum efficiency. And each beam removed seems to speed up the process like clockwork. Seeing a multi-story frame collapse in orderly sections feels like tipping giant dominoes, one careful push at a time. Debris is moved aside using excavator buckets, keeping the workspace clear and maintaining safety. Each cut is inspected visually, Any misalignment is corrected before moving to the next segment. The operator's experience and the TSW650XCV's robust design merge to convert chaotic structures into manageable debris piles. By the end of the session, what once was a dense construction area is reduced to clean, segmented material ready for removal. That balance of controlled force and speed is oddly satisfying, almost like a giant puzzle falling perfectly into place. The Okada TSW650XCV demonstrates how modern demolition relies on a mix of raw hydraulic power and operator skill. Repositioning, adjusting pressure, and sequencing cuts highlight both the engineering of the cutter and the dexterity of the operator. Each building or steel frame dismantled shows the versatility and reliability of this system. NNN. There's a strange thrill in seeing structures fall exactly where planned. Even a stubborn steel plate bends without hesitation. Watching debris settle into neat piles feels strangely methodical. Who knew demolition could feel this organized yet fast-paced? You almost forget how heavy and stubborn these structures were before the first cut. A John Deere tractor is actively engaged in ditch dredging or roadside clearing, using specialized attachments mounted both at the front and rear. At the front, a large auger-type tool rotates steadily, excavating soil and debris from the ditch or road edge with precision. At the rear, a similar attachment is connected to a conveyor system, which efficiently transfers the excavated material into a dump truck following behind. This coordinated operation not only clears obstructions, but also facilitates the maintenance of drainage systems, ensuring proper water flow. Such work is essential for land preparation in agriculture or site development and construction.
Though built like a fortress, the CAT D11 moves with balance and ease across demanding terrain. With 955 horsepower, load-sensing hydraulics, and a single reinforced chassis, it pushes efficiency to new ground. That push speed almost looks unreal when the ground folds beneath it. Larger blades move more material in fewer passes, lowering cost per ton. Feels like pure force made smart. Bushed pin bores and powered ladder access complete a design built for endurance and total control. NNN.
What makes the watermark track stable after reconditioning despite heavy loads and repeated traffic? Crews focus on track reconditioning and tie-in operations, ensuring the line will carry trains safely once reopened. Workers start by removing worn rails and timber sleepers, clearing space for replacements. Excavators and rail-mounted machinery lift old materials, stacking them in organized zones. Seeing the old rails lifted so efficiently is oddly satisfying. New sleepers are positioned carefully along the track bed. Hydraulic clamps and rail jacks hold them in alignment while fasteners are attached. The crew checks spacing and level repeatedly, maintaining strict adherence to standards. The precision needed to fit each sleeper makes the entire operation feel like giant mechanical Lego assembly. Once sleepers are secure, fresh rails are laid, guided by heavy-duty track-laying machines. Bolts and clips are tightened with torque wrenches to guarantee stability under heavy train loads. After the rails are in place, crews focus on tie-ins, where new track meets existing sections. Welding, grinding, and alignment adjustments smooth transitions, minimizing vibration and noise. Ballast is redistributed beneath and around sleepers, compacted to provide consistent support. It's surprisingly calm to see massive track sections aligned so neatly. Excavators and tamping machines work in concert, ensuring the track geometry remains within precise tolerances. Inspection teams monitor every stage, verifying track gauge, level, and alignment. Any deviation is corrected immediately, preventing future maintenance issues. Workers coordinate continuously, passing tools, operating machines, and communicating updates. Watching this teamwork in action is like seeing a moving puzzle solve itself. Debris and old material are cleared from the worksite, keeping the area safe and ready for reopening. By the end of the closedown, the watermark section is fully reconditioned, with new rails, sleepers, and compacted ballast ready for trains. There's a quiet thrill in realizing that this transformed stretch will soon carry hundreds of passengers daily. The teamwork on this scale is almost mesmerizing. Even the smallest adjustment contributes to overall safety. Rail replacement can feel surprisingly fast with the right coordination. Each tie-in point connects the past track to the future. The precision of alignment is impressive, without even being flashy. Seeing heavy rails move smoothly gives a strange sense of control. A section that looked worn and fragile now feels rock solid.
Sharp and methodical, the Placer RM 80-92U operates along the railway, restoring ballast with striking efficiency. Its cutting chain digs below the sleepers, scooping up the old ballast for cleaning. The material passes through vibrating screens that separate fine dust and oversized stones. Only ballast of the right size continues down the conveyor, where it's cleaned and redistributed under the sleepers. Oversized fragments are carried aside, while smaller ones are removed completely. That smart sorting makes the track foundation solid again without wasting material. Relayed ballast is leveled and compacted to form a uniform bed, ensuring stability for passing trains. The continuous movement of conveyors, screens, and hydraulic arms keeps the process smooth from start to finish. You'd never guess this much coordination happens under a single rail line. By the end, the renewed track is clean, resilient, and ready for heavy traffic again.
Follow the rollers as they methodically compact each section of the road base in Hartmannsgrund. Pavers distribute asphalt evenly, while rollers follow closely to compact it into a stable base. The initial action involves spreading the binder layer over the prepared subgrade, ensuring uniform thickness and smoothness. The coordination between the pavers and rollers keeps the process flowing efficiently. Engineers monitor the temperature and consistency of the asphalt mix, making adjustments as needed to maintain optimal compaction. Each pass of the roller increases the density and strength of the traction, forming a reliable foundation for the upper layers of the road. Seeing the material transform from loose asphalt to a solid base makes the effort tangible. Once the binder layer is fully compacted, crews inspect the surface for evenness and any imperfections. Minor corrections are made before moving on to the next layers. The combined work of operators and machinery ensures that the foundation meets engineering standards and will support the use of traffic. It's hard to imagine such smooth compaction of the machinery of this size. The way each machine aligns with the next is surprisingly elegant. Project Q1051 in Northern Australia involves the installation of large-diameter steel tube piles up to 12.5 meters in length to support infrastructure associated with an LNG processing plant. Each pile is fabricated from grade S355 steel welded into a closed-end tube U 750 mm, wall 25 mm, with an axial capacity exceeding 2.5 meganewtons. A crane-mounted high-energy hydraulic hammer initiates the primary impact driving phase, delivering sufficient blow energy for penetration through medium-stiff lateritic soils. Where noise limits or vibration sensitivity exist, a variable moment vibratory hammer is employed for pre-driving and final seating. Installation is staged. First, a guided pre-drilling pilot hole, then setting the closed-end pile within a leader frame. Impact driving continues until predefined refusal resistance is reached. A CapWAP analysis of the driving data confirms adequate sleeve and toe embedment, while wave equation simulations verify that stress levels remain within allowable limits for large piles. Throughout driving and drilling, each pile's energy, velocity, and estimated capacity are logged via a pile driving analyzer, PDA. Selective static load tests are conducted post-installation to ensure compliance with Australian standards and project specs. Avature.com. Site conditions, namely poorly graded sands and a shallow groundwater table, approximately 3 meters deep, necessitate pre-drilling or jetted entry to reduce resistance. Epoxy coatings are applied to piles in tidal zones to resist 50-year corrosion. Soil displacement due to impact compacts surrounding strata, increasing shaft friction by up to 30% and enhancing foundation performance, especially critical for a tropical, cyclone risk environment. This method delivers uniform settlement, high reliability, and reduced installation time for critical foundations long-term.
Operators and heavy rigs work in sync as the HDD reamer completes the last well expansion beneath the surface. At this site, horizontal directional drilling, or HDD, drives through layers of soil to form a well part of a new water supply system. The project is now in its third stage, the final well expansion. Each setup is carefully aligned before drilling starts to maintain accuracy over long distances. The reamer is prepared and connected to the drill string. Before connection, each joint of the drill rods is checked for thread integrity and lubrication. This large cutting tool enlarges the pilot hole to its target diameter. Once engaged, it rotates steadily underground, breaking and displacing the soil. You wouldn't expect such a huge tool to move that smoothly under all that pressure. The slurry system continuously removes the excavated material as the reamer advances. Pumps regulate the flow of drilling fluid to maintain pressure balance inside the bore. Before every run, the tool's bearings and cutters are rechecked to ensure no debris affects rotation. Operators monitor torque and pull force closely from the control cabin. Every turn and adjustment helps prevent misalignment or excess stress on the drill rods. Communication between the rig team and cabin is constant throughout the process. Once the full length is reamed, the well's interior is checked for uniformity. The diameter must remain consistent to fit the HDPE pipe that will later be pulled through. A deviation of even a few millimeters could cause problems during the pullback stage. Survey tools are often used here to confirm the alignment matches design coordinates. The drill string is then retracted slowly, completing the expansion. N Grigenic N. The HDD method remains one of the safest and cleanest ways to install pipelines without open-cut trenches. Imagine the mess if this had to be done by digging the whole street up instead. It saves both time and environmental disruption, which is why many urban projects rely on it today. That moment when the reamer breaks through at the exit pit always feels like victory underground. Once confirmed, equipment is cleaned and prepared for the next phase of pipe installation. NNN.
Precast Concepts ensures each manhole installation seals perfectly and efficiently with the Hamilton-Kent 3S push-fit connectors. These pre-lubricated connectors link directly to the concrete base, while PVC pipes fit effortlessly without any boot tightening, making the installation both precise and reliable. Before connecting, operators measure the pipe length carefully to account for the portion that will sit inside the concrete base. After cutting, the pipe ends are chamfered and deburred, ensuring a smooth connection surface. Didn't expect how easily the pipe slides into place once lubricated. The spigot end of each pipe is slowly inserted into the bell end of the downstream section and firmly pushed until seated, creating a watertight seal. Untitled. When placing the precast concrete base into the trench, proper lifting clutches secure the load. Operators verify the trench bottom is clear so the base sits level. Both the downstream pipe and the base outlet are lubricated, then aligned, and the manhole base is lowered until the pipe is fully inserted. Adjustments ensure proper leveling. This setup makes the manhole fit like it was custom built on site. NNN. Upstream pipe installation follows the same steps: measure, cut, chamfer, lubricate, and align. The pipe is inserted until it firmly contacts the rear of the third step of the base outlet. A final check guarantees both upstream and downstream connections are watertight. Hydrocarbon-based lubricants are avoided to maintain connector integrity. Feels like a smooth choreography of precision and strength, even though the mechanics are simple. Printer glides along foundation, shaping the home. Habitat's 3D printer in Williamsburg lays the first concrete layers of a new house, building walls directly on the foundation. Operators monitor alignment as the printer deposits each layer, ensuring structural integrity. The concrete is prepared and guided for smooth placement. The pace of wall construction is faster than expected for a home this size. Sensors track each contour while layers cure. By day's end, the basic structure stands ready for finishing. That printer makes building look almost effortless, like a giant Lego set. Building a custom pool has never looked this approachable, thanks to Megapool EPS blocks. These blocks, EPS 25, with an internal 10mm layer of EPS 80, form smooth, even walls for a separated pool structure. Workers begin by marking the pool's layout on the ground, checking alignment and level before lifting the first row of blocks into place. Each block interlocks precisely, ensuring a uniform wall surface. It's satisfying to see the walls grow so evenly. Once the base row is set, additional rows are stacked, with each block pressed firmly against its neighbor. These blocks are surprisingly sturdy for their weight. The lightweight EPS material allows workers to maneuver blocks easily, without heavy lifting equipment, yet the rigidity ensures stability. For corners and curves, blocks are cut to size, maintaining smoothness and consistent thickness. The cutting process looks oddly satisfying. The way these blocks slide together makes assembling a pool look almost like playing with oversized Legos. After stacking, the walls are checked with levels and straight edges to confirm verticality. Connections between blocks are sealed with adhesive designed for EPS, adding structural cohesion and watertightness. Seeing the adhesive fill tiny gaps shows attention to detail that pays off. Internal EPS 80 layers enhance insulation, keeping pool water warmer and reducing energy loss. Workers inspect each section before moving on, preventing alignment issues from compounding. That moment when a row lines up perfectly gives a surprising sense of accomplishment. The final stage involves finishing the walls with plaster or a protective coating. This ensures a sleek, clean surface that is safe and visually appealing. Lubricated tools help smooth the coating evenly, filling any minor gaps between blocks. The wall finish ends up looking smoother than some commercial pools. During the process, workers coordinate efficiently, passing blocks, applying adhesive, and smoothing surfaces in rhythm. Seeing everyone move in sync without verbal cues feels oddly like a mini assembly orchestra. Watching the pool come together this way shows how simple modular construction can produce professional results. The EPS system really allows for quick adjustments if a block is slightly off. Throughout assembly, the Megapool system proves flexible for custom sizes and shapes. Pools can be expanded or modified on-site by cutting or adding blocks, demonstrating the versatility of EPS construction. It's amusing how quickly a small team can erect a full-sized pool. By the end of the day, the pool structure is fully formed, ready for water installation. Eden. This method almost makes pool building look like a weekend hobby instead of a construction project. Who knew pool building could feel this controlled yet fast, almost like building a mini fortress for relaxation. Even the corners and curves fit seamlessly, which is a neat trick for modular construction. The process somehow manages to look fun while still being serious work.
Massive blocks of marble arrive at the caisson factory, each awaiting transformation into polished slabs ready for construction and design projects. Operators coordinate the unloading carefully to prevent cracks, showing a respect for the material's natural structure. The blocks are then placed in a block stockyard arranged by size and quality, allowing workers to select the right piece for each order. N. Water-fed saws slice the marble blocks into slabs of precise thickness, maintaining structural integrity. Every block seems to rest perfectly in place before the saw engages. It's remarkable how controlled the water flow is, keeping dust low while cooling the blades. Each cut is guided automatically, reducing manual intervention and keeping the output consistent. The slabs pass to processing plants, where polishing machines smooth surfaces and highlight the stone's natural veining. Polishers adjust speed and pressure to accommodate the unique texture of each slab. Workers monitor the process, ensuring that nothing disrupts the smooth progression of slabs. After polishing, slabs are inspected for imperfections, with defective pieces separated to ensure quality standards. Robots assist in lifting and aligning heavy slabs, reducing strain on the workforce. Stacking patterns are repeated carefully to maintain balance and airflow. From inspection, slabs move to storage or are prepared for shipping, stacked securely for transport. Operators ensure the stacking maintains airflow, preventing potential warping. Office personnel coordinate orders and logistics, tracking inventory from saw to shipment. The seamless flow between stockyard, processing plant, and packing area maximizes efficiency. Drum Marble's commitment to quality is evident in every stage, from initial block unloading in Kishingar to finished slabs ready for customers. Even slabs with complex veining maintain structural and aesthetic integrity after processing. Every step reflects years of refinement in machinery setup, worker skill, and workflow organization. This factory has grown into a benchmark for marble processing in India, handling volume without compromising finish. Coordination between mechanical cutters, polishers, and manual oversight produces slabs that meet precise architectural specifications. The end result is marble that's both durable and visually striking, ready for installation.
Splitting granite is a time-tested process that combines technique, force, and an understanding of natural stone grain. One of the most traditional and effective methods is to use a feather and wedge, also known as a plug and feather, along with a hammer. The process begins by marking a line along the surface of the granite, usually the location where the split is to be made. Along this line, a series of evenly spaced holes are drilled using a hammer drill or chisel, typically spaced about 10 to 15 centimeters apart, and approximately 1/3 the thickness of the stone. Next, a pair of steel feathers' thin metal shims are inserted into each hole, followed by a wedge in the middle. This forms a three-part system that, when tapped, directs pressure outward into the hole wall. Using the hammer, the operator gently and evenly taps each wedge in sequence, moving along the desired split line. With each tap, the tension is gradually increased across the granite slab. Eventually, the internal stress exceeds the rock's capacity to withstand it, and it splits cleanly along the drill line, often with incredible precision. This method requires patience, time, and a feel for the material. It is still widely used today in stonemasonry, monumental carving, and architectural work due to its simplicity, precision, and minimal material loss.
See how the Darda C12 quietly splits solid rock on a Swedish construction site, showing how controlled power can reshape the ground. Unlike traditional blasting, this hydraulic splitter operates quietly and without vibration, allowing work near existing buildings. The process begins with drilling several holes into the rock surface, forming the placement points for the C12's expanding wedge system. You wouldn't expect such a small unit to break granite this cleanly. Each wedge assembly is inserted and pressurized by a connected hydraulic power pack, generating up to hundreds of tons of splitting force. The rock cracks along predetermined lines, separating large sections without shockwaves or flying debris. That split sound feels oddly satisfying, just controlled power doing its job. Operators reposition the splitter along the rock line, repeating the expansion sequence to achieve full separation. The absence of noise and vibration protects nearby foundations and underground utilities. Once the main blocks detach, smaller sections are lifted and removed using excavators. This method looks calm, but moves a huge amount of material fast. The Darda C12 is lightweight enough for a single operator to handle, making it ideal for confined areas. No dust clouds, no heavy impacts, just steady progress through solid stone. Its hydraulic system delivers consistent performance, even when dealing with dense rock types. The result is an efficient, controlled excavation that keeps both workers and surroundings safe. You could almost call it the polite way to break rocks.
In the quarries of Culebrillas, Arequipa, Peru, the age-old craft of carving siller, a soft white volcanic stone, continues to thrive entirely by hand. One artisan, originally from Chiclayo and Piura in northern Peru, moved here over 15 years ago after meeting his wife in Lima. Drawn by work opportunities and a strong tradition, he left fishing behind and embraced a new life in stone carving. The process starts by marking the rough stone block to define the desired size of each siller. Using a combo, a heavy hammer, artisans carefully sculpt and shape the stone, often turning it manually to work from different angles. To guide the dimensions, they use rubbers, homemade measuring frames crafted from repurposed plastic bottles. With steady hands and practiced precision, he strikes the surface of the raw siller stone. Blow by blow, the chisel cuts into the surface, gradually shaping the block into its desired form. Each strike is deliberate, controlled, and refined through years of experience. The stone begins to take shape, edges straightened, surfaces leveled. It's a rhythmic, physical process requiring focus, strength, and technique. This handmade approach ensures consistency without the expense of machinery. Though machines can technically carve siller, the traditional method remains favored for its lower cost, rustic appearance, and cultural significance. Machinery involves additional expenses, fuel, cutting discs, and maintenance, which most craftsmen cannot afford, especially when buyers aren't willing to pay more. Once shaped, each stone sells for about 1.5 USD directly at the quarry. After deducting personal expenses, a typical monthly income ranges about 300 USD, varying with workload and weather. Everything, from splitting and shaping to final detailing, is done by hand, a true testament to artisanal skill passed down through generations. In a world of mechanization, the siller quarries of Arequipa remain a powerful symbol of craftsmanship, resilience, and the enduring connection between people and the earth they shape. Creating flawless countertops becomes manageable with the miter system by Integra. The process starts with cutting the edges precisely, using surface bonder sheet to ensure a smooth joint. Each cut is measured carefully to align perfectly with adjoining pieces. The precision here is key. Slight misalignment can ruin the final edge. Once edges are prepared, clamps hold the pieces in a dry fit. This step allows workers to verify alignment and fit before applying adhesive. The dry fitting stage reduces errors and ensures surfaces meet cleanly. Some pieces might need micro adjustments, and the clamps make these corrections simple and controlled. It's satisfying to see the edges align so perfectly, almost like a puzzle snapping together. Gluing follows next. Surface bonder sheet spreads evenly across the joint, bonding the miter edges into a solid seam. Operators apply consistent pressure, keeping surfaces flush. The adhesive cures quickly, forming a durable and neat joint that will withstand daily use. Never expected glue to hold such heavy materials so seamlessly. Finally, polishing smooths the surface, revealing a seamless countertop edge. Polishing tools remove minor imperfections and create a professional finish. The miter system simplifies what could be a complex fabrication into 4 organized steps, allowing even small workshops to produce high-quality results. That polished edge looks almost like it came from a high-end showroom. Throughout the process, Integra's design ensures each step complements the next, reducing mistakes and improving efficiency. By the end, what started as separate slabs transforms into a continuous, beautiful surface ready for installation. This system makes countertop fabrication almost fun to watch, like building with giant, elegant Lego blocks. And